Okay. So yeah, there's an interesting question in the chat about SV19 and lab goggles. I just emailed the stockroom for confirmation, but my understanding is if it's open, they will be selling them. If that changes, if I get notification to the contrary, I'll let everybody know. But as I mentioned last week, we're going to start things slow when it comes to the lab. And so what that means is that we're not going to jump right into an experiment. We're going to do safety discussion, just point out the things in the lab about where to go if under certain scenarios and what to do under certain procedures, that sort of thing, kind of like what we talked about lab experience week 1. And then you'll take your second quiz, which will be in person and handwritten, that sort of thing. Much nicer than a Canvas quiz. However, we still will be doing an experiment. The experiment is going to be a simulated experiment. And then we'll roll into in-person experiments starting next week if everything goes smoothly. So our experiment 2 is on density. And we had previously talked about density in our lecture. This gives us an exploration about how do we take the measurements to calculate density, and how do we interpret things about density. So the goal of today's experiment, or this week's experiment, will be to practice recording the measurements for density and then putting that to use. And sorry, I'm a little bit distracted, but I just got the email confirming, yes, you can go to campus if you are have been tested, and you can buy your goggles. Oh, and apparently the price has changed to $5, so it's actually $1 less than what I said. Again, remember it's cash, so you'll just need a $5 bill. Okay, well, I didn't know about that. Okay, sorry, so good news. But what we're going to be doing in this investigation is actually using several different tactics to record the measurements necessary to find the density. Remember that density is the mass of the substance divided by the volume of that substance. So there are different ways that we can do that depending on the type of substance, the thing that we're investigating. So the first method is measuring how do we measure liquid densities? And so for that, we're going to be using graduated cylinders. So a graduated cylinder is a tube, a container that has tick marks indicating volume amounts. It measures volume in milliliters. It's read the same way as a ruler, meaning we do have to be careful about how many decimal places to go. Depending on the tick marks, it might not be the same decimal places as your ruler. Remember, we should actually practice each time going through the sort of scenario, right? We ask ourselves, how much does each tick mark count? And we can always go 1 decimal place more than the tick mark. And that's because we can always estimate this little space in between the tick mark. So we just want to be careful because we can't take it for granted, or we can't always assume it's the same every time, because different instruments will have different spacing countings of the tick marks. So one might be counting the ones place, the other might be counting the first decimal place, 0.1, 0.2, 0.3, 0.4. So we have to just be mindful that we don't always assume it's going to be the same every time. We have to look at the tick marks and figure that out. That being said, we are going to use the graduated cylinder to measure milliliters, and milliliters is a measurement of volume. So that's one of the variables for density. The thing that makes this a unique scenario is that because it's a liquid, we can easily pour it into a container to measure its volume. We can pour it into a graduated cylinder and count the tick marks to see how much it is. The question is, we also need the mass of a liquid. And if you've ever tried, it's pretty hard to just pour a liquid onto a scale and try to read it. So how do we get the mass of a liquid? How do we do that? And I give you a hint for any of you who are cat owners. I myself am a cat owner. What's the easiest way to weigh your cat? So we want to get its weight, or rather its mass to be technical. But how do you do that for a liquid? And I say, well, how do you weigh a cat? Is anybody out there a cat owner? Has to take it to the vet maybe sometime.
You subtract the container mass.
Mm-hmm. Yeah. And so what I was getting at with the cat thing is that, cats often don't go where they're supposed to. So when you weigh them, you have to hold them in your arms and then you both go on the scale and then you subtract your weight. It's the same thing with this. In this case, we're the container for the cat. In the lab, when we want to measure the weight of a liquid, we're going to do the same weighing. We call that the weighing by difference method. Especially important when we are talking about substances that are messy and we need to weigh them. We can sort of visually see why this works, because we could say substance, there's some substance, if I put it into a container, so there's my best attempt at doing that. Well, the substance plus the container on the scale, if we subtract the container, then we just get the substance. So what we're doing is we're practicing thinking about how to solve sort of problems in the lab. If I need to weigh a liquid, it's going to get all over the place. If I just pour it onto a scale, it's going to drip. We're going to lose some. So instead, what we do is we use a container that we've already weighed, and then we weigh the substance inside that container, and we subtract out the container's weight to get the substance. And I should mention that what I'm talking about here is weight. And so that's exactly what we do for the first method. The second method is for what we call regular objects, objects whose volume can be calculated from measuring dimensions and using commonly known formulas. So this is important for solids that have regular shapes. So we're talking things that are sort of box-like, things that are cylindrical, things that are spherical, because we need to know density from its mass and its volume. In this case, well, since they're solid objects, they're very easy to put on a scale and weigh them. In the case of volume, if we have a regular object, we can take down the measurements that we need, the dimensions, to figure out the volume in this case. So this is kind of the standard when we think of getting the density of something. Well, we can measure the dimensions of the object to get its volume. And so just a reminder on these volume formulas, for a box-like object, volume is length times width times height. And by the way, I didn't have a chance to put the slides on for this one beforehand, so they're going to come later. but they'll be on the current modules that we are doing. In this case, for a cylindrical object, we need to measure the radius. So remember the formula, it's base times height. In this case, the base of a cylinder is a circle, pi r squared times the height. And then finally for a sphere, we also need the radius of a sphere. Remember, this is the radius. The volume of and I should probably label sphere. This is for a cylinder. This is for a box. It's 4/3 pi r cubed. And this 4/3 is a formula number. So we know what that means when I label this kind of number a formula number when it comes to doing the calculation and rounding our final answer. It means we should think of this 4/3 as having infinite sig figs, meaning don't worry about this portion, worry about the sig figs of my radius to find the answer. Since this is all multiplying, we're rounding to sig figs. So that's the second method. You have a regular object, then you're going to measure its dimensions and then plug it into a volume formula. The third method is for an irregular solid. So how do we get the density of that? So what does irregular mean? It means an object with shapes that don't have commonly known volume formulas. So imagine that this is a solid, but it's definitely not a cube or a box or a sphere. But if we want its density, we still need to know, its volume. So brainstorm, how do we find the volume of something like this, where we don't have a volume formula that we could say, oh, just measure its diameter or measure its length. Think back to the pogo, right? So it's the same thing as the pogo. When we don't have a formula to use for dimensions, instead we can use, remember this is called volume displacement. This works when we completely submerge, emphasis on completely submerge the object, then the water level in the tube is going to rise. This difference is the volume of the object. And it works, it kind of like as a visual way to show it, it works the same way as the weighing by difference. In the volume displacement method, what we have is once the object is submerged, this amount of liquid is indicating how much liquid and object volume there is. Liquid plus object. If prior to dropping the object in, we know the volume of the liquid minus liquid gives us object volume. So that's the key to volume displacement. Again, the idea is you have to know something beforehand before performing. In this case, we need to already know the volume of the liquid. So we have to read what it says before dropping it in and then see how it changed after it drops in. But it works the same way. If I know the liquid and the object's volume and I subtract the liquid, I'm left with the object. And so that's how we get the density of an object in all three cases. Density of a liquid, density of a regular object, and density of an irregular object. Now, there's a really good question in the chat. What if it floats? Because I mentioned something important was that we have to completely submerge the object in order to do this. Because the formula, well, implicitly, the formula says, however much mass that object is, we have to also consider all of its volume. So if we sort of play around with the idea of volume displacement, the more, if I stick my finger in the water, the more I push down, the more volume it displaces. So it does depend on having the whole thing submerged to get the whole volume of the object. If it floats, then that means we can't trust our answer because we're not putting the entire object in there. So we can't use volume displacement for an object that is currently floating in the graduated cylinder. However, can we brainstorm a way that you could still do volume displacement with an object that floats? Because there are still ways we could do it. The key idea is that in order for this to work, the whole thing has to be pushed down. So any ideas what we could do?
I guess like add a heavy object like above it and then subtract that for the heavy object for them.
Yeah, we could force it down by sort of putting something more dense on top of it, pushing it down. And then if we know that object's density, or sorry, if we know that object's volume, then we could just subtract that. So we could either pick a regular object where we could get the density, or I keep saying density, volume, or we could use a volume displacement to find the volume of our second thing, and then we can put one on top of the other. It pushes down, and then we could just say subtract all of it. Liquid plus object plus, I'll just say weight. And by weight, I mean a thing that is like a paperweight, a heavy thing. And then if we subtract the liquid, and then subtract the weight, then we get the object. And I should say volume. Yeah, so that's a very good point. What happens if it floats? Well, we can't use volume displacement as is if it floats, but we could do some tricks to help us. One thing is we could sort of weigh it down with something that has a known volume. Then we just subtract out this weight, and we subtract out the liquid, and then we get the volume of the object that floats. And in the POGL, you had the ability to use your mouse to pull the object all the way down so that it would get the total volume of the simulated objects. So those are the three methods. Again, this is going to be a simulation. So you're going to be sort of presented the scenarios, and then you do the analysis. So you're going to calculate the density by the three methods. In this case, you're going to be given sort of the images of the objects, and you're going to have to read the ruler. You're going to have to read the graduated cylinder, and then you're going to have to do those analyses for the regular, irregular, and the liquid density calculations. Then you're going to calculate for some of them the percent error for the densities, because some of these are objects that you know. For example, the liquid you're going to measure the density for is going to be water. We know what the density of water is. So the question is, do our measurements have a large error to them by checking using the equation for a percent error? Just a reminder, the percent error is in lecture 1. It was an example of mixed math, meaning that when you're doing the calculation, you shouldn't put it all in your calculator at once. You should go step by step, because we want to round to correct final answers. And again, when you mix the math, you have to do one step at a time. Conceptual understanding of density. So putting together, now that you have your density numbers, the idea from our lecture 2 where we talked about, what does it mean when something floats versus something sinks, that sort of thing. And then error analysis. And so error analysis is what would be the effect of something going wrong while you did the experiment. That's something that's going to continue when we do our in-person labs. If you didn't get the answer you thought you were going to get, well, what could be the reason why? And so just to give an example of how an error analysis looks and how it should be sort of stated, I'll give an example scenario. Imagine we have this regular shaped object. We want to know its density. So I'm going to record the dimensions. I'm going to write down the properly rounded length, width, and height. So that will be what I need to get my volume measurement. That will then go into my density formula. But say something happens on the way there that I don't notice. I don't realize that my object broke. It chipped. So it did this right before I was going to put it on the scale to weigh it. So this is the sort of setup for our error analysis. I have lost a little bit of my object. Now the question is, what will the error do to my measurement, and what will it do to my final answer? So there are always going to be at least two sentences when I ask you an error analysis question. One is, what measurement does error affect? And two, what happens to final answer? And by that, I mean too big or small. What did it do? So the first part, so this is my scenario. I had this cube. I measured its length, width, height to get its volume. And then before I put it on the scale, it actually chipped. And then I weighed it. So what measurement does this error affect is the first thing you have to identify when given an error analysis. So not just I messed up, but what did you mess up? What happened? What did it immediately affect? So this one might be a little bit apparent, but obviously if I chip off a piece and then I weigh it, mass is less than the true mass. Let's say the true mass. If I take off a piece of this object, then it's going to weigh less. So the immediate effect is the mass is going to be less than the true mass. Now, the second part, there's always going to be two sentences in an error analysis. What measurement did it affect? And then what happened to the final answer? In this case, it's the density. So we can often start with, because the first part, our mass is smaller, what should happen to the density? Or I should say the density calculation will be what? Too big or too small? D equals M over B. Too small, right? One thing to note is that, I'm looking for your final sentence, but on a scratch paper, you could practice sort of what will be the effect. You could put in sort of example numbers just to double check. If I put a 1 here and a 2 in the denominator versus 0.5 on the top and a 2 on the bottom. You could double check, but yeah, it will be too small because if I put a small number out here and I just use example numbers, it will be definitely small. Will be too small as a result. So instead of having the true density, there's an error. This error will make my final answer of the density smaller than it should be. So whenever there's an error analysis question, the way to answer it, to respond to it is, well, what will having this accident or whatever do to the measurements? Like what I am actually going to record in my notebook, then how will that affect my ultimate goal? Well, I was going to use the mass to calculate the density. So if the mass ended up being smaller than it should be, then my density is going to be smaller than it should be as a result, because mass is in the numerator of the equation. Again, this is going to be a simulated experiment this time. When we get into the lab, we're going to take it slow and not do too much, just in case. And then we'll pick up on our other labs in person on our next week. The actual module for experiment 2 will be opened on lab day. So you'll, much like before, when it comes to simulated experiments, the at-home experiments, I give the whole week for that. So once it's open on lab day, it'll be for the next week. However, it's a good idea to get a head start on those. I like being generous when it comes to the due dates of the simulated labs, because I know you might have questions and so forth. But yeah, that's how it's going to be. With that is the experiment 2 on density in summary. Now at this point, I'm going to go ahead and pause in case that there are any questions about what I just went through, or can you explain how to do a weighing by difference or a volume displacement one more time, et cetera, or error analysis and so forth. So I'll give you guys a second if there's anything to ask about that. Okay. Okay, so I have two good questions. One is about the error analysis. So just to emphasize what error analysis means is it's not just saying, oh, here's where I went wrong. It's saying that and explaining why it mattered. So notice that's what the 2 sentences are that you're going to have to show. What did it do? What did the error do? And why should we care? So in this case, if I accidentally broke my object, then the mass would be lower than it should be. And it mattered because mass goes into the top of this formula. My density is going to be smaller than it should be. So I made a mistake and it made my final answer too small. That's the error analysis. But very important to talk about. Thank you. The second question was about the COVID test. So the COVID test, I have not heard any indication that you're allowed to do a take-home test. I think you're supposed to do it the rapid test at a facility. Yeah, that brings me to, did anybody have any trouble getting their test on the weekend? I went yesterday, and what I will say is go early. That is my advice. So yeah. Yeah. So I would double check the wording of the website, the PCC's website about that. What I now that the PCR tests tend to be more sensitive than the rapid test. I don't know if they're interchangeable. What I will say is that if you do it through PCC, it's a very straightforward process. So, just to give you my experience, I went half an hour early. I barely had to wait. But by the time I was done, the line was huge. And so this was at the mirror pools. So the front that faces Colorado Boulevard. I wait there. They need a photo ID. I showed them my photo ID. They gave me a little tube. Within a minute, there was a nurse who was administering the test, the swab. And then 20 minutes later, I got the email for my results. So as long as you're okay sort of getting there really early, the PCC method, the PCC is pretty straightforward. If you do it at, if you can make an appointment to do it somewhere else, it just needs to be forwarded to PCC through that website link that I gave. So yeah, if you're going that route. But that being said, the PCC, it was really fast. And the only thing is the wait. So, but once you actually go in there, you go and get seen by the nurse, it's extremely fast. But that being said, don't wait, don't hesitate. If you have nothing to do today, you might want to go, sooner rather than later, and so forth. I'm also hearing COVID clinic is also giving quick results. And yeah, the testing is all throughout the week. It just depends on when your first day of class is. So it just has to be within 3 days of the first time you're going to enter the campus. So if you have a different class that meets earlier than our class, then you just need to be 72 hours from the first time you set foot in PCC. The whole rest of the week, that test is still valid, so you don't need to take another test if you're going to come to campus at the end of the week, for example. Yep. And the schedule for testing is I linked that website that said the testing schedule, but they're using lot 3 for drive-through, and then the mirror pools for walk-in testing, which I'm an advocate of the walk-in one, actually. Like I haven't experienced the drive-in from PCC, but just seeing the line of cars versus the walk-in, that might be a better option if you can just park your car, or if you can just be on campus, and that's a really nice way to do it. Okay. Anything else? We're gonna have a good first day. I'm gonna send later tonight a reminder about things to bring tomorrow, like bring a pencil, bring a calculator, bring a mask. Yeah, so it's the sort of, question is, where exactly is the walk-in? So it's the sort of the ponds. We're talking about those ponds that face Colorado Boulevard. And it's like adjacent to the quad area. I'm hoping that they have more signage because it was kind of difficult to figure out where to go at first. And then you just see, oh, there's a long line of people. Maybe I should just stand there. Okay, so I'm going to go ahead and stop the share and the recording for right now. But if there are still questions, please let me know.